Archiving started.
Okay. All right. So this is a talk. I basically just kind of threw this together, and I used some of my previous stuff, and I put in some new stuff and made a few changes. So if any of this looks familiar, that's why. But the real focus here is really on the new project I'm doing, which I'm applying for a couple grants on. Right now, the first application deadline is going to be for a NASA grant for the Rose's astrophysics theory, and then this also may be of interest to the NSF. So the whole idea of this is to look at gravitational radiation, which is produced by primordial turbulence. And this is some work that other people have been involved in over the years, but there really hasn't been a fully numerical, any really fully numerical work done on it now. And so there's sort of a niche and a lot of room for improvement with this, but we'll see exactly what develops. So this is a brief outline. First thing I want to do is go over just basic review of some of the cosmology and the primordial turbulence, and also a little bit about background about gravitational waves and what they are, just sort of a reminder. And then I would get into the research objectives, talk a little bit about what we need to do for initial data, talk about how the numerical evolution works, what needs to be done for data analysis, and then other future developments. And also this will include a few test results that we have so far. Me and some of the graduate students who have worked on this in the past. Yeah. So this is going to seem somewhat elementary to some of you guys, but I figured it's better to review than to jump too much in. And when I give a talk for the APS, a lot of this background is going to be cut out. So this is the history of the universe as seen according to cosmologists. So basically, we're up here at the top. Yeah, this is all 7 days. So we're up here at the present, and we look out with telescopes. And then the further you look out, since the speed of light's finite, you're looking back in time. And so what happens is if you look back far enough, you see older and older stars. But what happens is the universe is believed to be about 14 billion years old. And so if something is a billion light years away, then you can only look back in time about to the universe about 13 billion years old. Now, if you go back enough and you use astronomy techniques, you can get back to around this 500,000 year point.
Can you actually see how far back can you see if you've got that observational horizon?
Yeah, and actually that depends on the power of the telescope, but really, in theory, since inflation was so early on, you could see 13 billion years. Yeah, but in practice, what happens is there's an even worse horizon here because before this point, the universe was so dense that light could not make it through without scattering. So this is called the surface of last scattering, and this is, or before this, you could say the universe was just opaque. So what happened here was, if you look at the cosmic microwave background radiation, this is the part of the universe it tells you about. So when they say that we're studying the early universe by looking at the cosmic microwave background radiation, it really leaves out all this stuff. It's really just talking about this part, and they're kind of deriving what happened here from basic physics principles. So they're really not seeing anything earlier. And if you put in experiments like the LHC and plasma physics experiments, you can kind of learn about the physics earlier on, but you're not really observing it. What we're going to do is we're going to go all the way back to here. So we're going to skip ahead add another half a million years onto what's observable, and we're going to get within the first 1 second of the life of the universe through direct observations through these gravitational waves. And the reason why, I'm going to get to later, but with gravitational waves, they're not scattered. They don't, they're not easily absorbed by anything but a black hole. So when you see the gravitational waves, you're seeing them from the moment they were created, instead of from all the scattering that's happened since. So, you know, cosmic microwave background radiation up here, gravitational waves somewhere down here. And neat thing too, which I'm going to get to, is that a lot of these gravitational waves were created during the electroweak era. So we're directly studying electroweak physics, which only the LHC can do right now. And we should be able to do all that through direct observations. But
what do you mean by direct observation?
no, we're not. It's not electromagnetic radiation which gets scattered. It's gravitational radiation. It's a completely different thing. So it doesn't get scattered. So you're really observing the gravitational waves directly, not after they've been scattered or anything like that.
At some point, really running on linear, then it's sort of scattered.
No.
It's not a linear way.
No.
And then it's scattered. But what is higher nonlinear?
When they're higher nonlinear, they get weaker and weaker and weaker, but they don't really scatter unless you hit it with something like a black hole or something to absorb it. So they're really
observation of gravitational waves that could potentially eventually get there.
Yeah, and I'm going to talk about how that works.
Don't have an observation of that, you know.
At some point, you have geometric dynamics.
But we'll talk about that. So anyway, the whole idea here is to be able to observe the universe earlier on and be able to tell things about the much earlier universe by using a different way. And it's kind of like if you know, if you have one type of signal only gets you so far, you switch to a different type. And gravitational waves are really far off from that. So here's just a quick view of what we believe happened in the really early universe with inflation theory. And so, as far as we know, the universe was tiny and it blew up. Long story short. So what happens here is the universe starts off at a Planck time, as we understand it. It was just kind of cruising along, and then something happened, and it inflated really quickly, grew up by several orders of magnitude. That stopped, and then it just continued moving along. And so the observable universe that we see now was much smaller than it is today. It took up a much smaller space. And inflation is used to explain how this thing happened. And the way that inflation works was, we believe there was a scalar field which created sort of a false vacuum, because instead of the ground state being at the ground, it was much higher up. And so this inflation, when you put it in with the general theory of relativity, basically says that if you have the right mass distribution, you cause space-time to curve or expand, and that caused a rapid expansion. And it's really interesting because the expansion actually occurred faster than the speed of light, which is allowable because it's not, the Einstein's speed of light only applies to things moving faster than the speed of light within space-time. If space-time moves faster than the speed of light, that's allowable. So space-time expanded faster than the speed of light, and you basically had the scalar field, and then outside of the scalar field, you had a real vacuum. And over time, as this thing cooled, the two of them sort of mixed.
Which field are you talking about?
No, this is a scalar field. Well, nobody knows exactly what the scalar field is, but it was. This is what's in the inflation theory. It could have been two fermion fields that were anti-aligned, or two spinor fields that were anti-aligned. It could be a lot of things, but then to make the theory work, you put in a scalar field.
And then we talk about scalar field. Scalar field is in a high energy physics, for example, there is always a zone of very unknown scalar field. Like, you know, when we keep on extending the...
Yeah, well, that's in here.
Yeah, so it could be anything which is not known. Even in a metric model.
Unknown force of nature.
Unknown force of nature. Unknown.
God, angels,
Which Garrison has tried to call as a source of gravitational force.
What happened? Yeah. So what happened here was really interesting. Is that if you have the scalar tunnel through to create bubbles within the scalar field. So you might have, within the scalar field, you might have bubbles of real vacuum. And eventually, as things cool down and the bubbles would collide and it would expand, and over time, this led to a phase transition where you actually went from having the scalar field pulse vacuum dominated universe to having a real vacuum. And that was sort of when the expansion ended.
Have any of these concepts like the depiction profile of the
Actually, I think when it goes to dark energy and those kind of concepts.
you see something, and there's no calculation for it in terms of any way, then are there predictions made from those things?
It's I think a lot of the stuff with WMAP was actually to verify parts of the theory.
Can we call it like, the gravitational waves as the vacuum fluctuation of this solid vacuum?
Well, it's actually more than that. There's several different sources of gravitational waves, but what happens is these vacuum bubbles are really an important thing because their collisions and their motions produce gravitational waves by themselves, but then also when they can actually stir up the material or the primordial plasma and end up giving you the turbulence. So these vacuum bubbles lead to one of the causes of turbulence. There's also, quantum fluctuations that got expanded during this stage, which led to, the density perturbations, but then they could also lead to gravitational waves. And so there's a lot of different things that happened in just this red point, which was well within the first second of the life of the universe.
Okay, what kind of plasma you are talking about?
In this case, any kind. But basically it would just be protons, electrons, the positrons.
Electrodynamic plasma?
Yes. Any matter that was in the universe when this thing was going on became turbulent.
Yeah, so it's not at that time.
Yeah. Actually, this is all seconds. So you can see that the universe, you got to get here to get to around 1 second. So we're talking about very, very far within the first second of the life of the universe.
So WMAP actually, the quantum fluctuation,
No. Well, the idea is that these fluctuations led to what we saw up here later on, which we observed with WMAP. So WMAP is basically looking at these effects propagated over 500,000 years. And what I'm saying is that we could probably do better than that. So WMAP is really looking at this and then trying to say, well, we're seeing this, and so therefore all this stuff must have happened earlier.
Anybody else in the proposal, or this is just?
This is background. But yeah, some of this stuff we have to put in, but some of it we don't. Like I have a more thorough explanation of how these these vacuum bubbles actually worked in my proposal, because there's a lot to the physics that isn't very obvious. Mm-hmm.
The electron positron type plasma, or whatever, I call it 2D plasma,
Yeah.
is relativistic plasma. And in relativistic plasma, usually there is an associated mass with a vacuum state, like scalar state.
Yeah.
There is an associated mass. And apparently it has to be very large mass to get a significant effect of the created turbulence in that plasma, because that's a relativistic plasma, and mass component is very small. Like if we are talking about electron positron plasma, they are very light particles. So it is something where we have to be like,
Well, you got to also keep in mind, if you go back this far, what's the density of the universe?
mass density is very low.
No, mass density in this case would be extremely high.
So, but still,
Mass energy density at this point would be incredibly high. Much higher than star density.
so actually, of course it is higher than that. But still it is like I said, both because of heaviness, that when we compare that density and temperature. That is the ratio which has to be done.
Well, I don't know. I can send you back to the literature. This isn't my focus here, so I don't want to argue with you on that. But the thing is that there's been several dozen papers written where they've talked about this and talked about the turbulence resulting from it. Anyway, what I did learn about primordial turbulence from reviewing the literature, first off, it's been studied by several researchers. I just got a hold of one of the people in the field. I'm going to be talking to him soon about, making sure to fill out any gaps I might have in my knowledge. But it's been modeled. Basically, what people have done is they've studied this effect of the vacuum bubbles, and they kind of want to see what the end result is. So it's been more in the cosmology than in the gravitational physics domain. And so what they've done is they've kind of tried to model the turbulence that would result from these vacuum bubbles. And you can come up with a pretty good, pretty reasonable estimate of how big velocity fluctuations would be within the fluid. And once they had that, they were able to kind of predict that, well, if you have this much energy in the plasma, it's assuming it cascades like we know plasma cascade from like something like John would work on, then you can calculate how much energy is dissipated from it and assume that energy goes into gravitational waves, and therefore the gravitational wave spectrum must be such and such. And so this is basically the way it's been done. And so there's they've used typically a non-compressible fluid or magnetofluid for their systems. They've kept it as just kind of a one-fluid system. There hasn't been any dark matter added in any of the literature I've looked at. They've assumed that the energy cascades the same as the non-relativistic plasma, which we don't know if that's correct, of course. And they also have been able to get from all this that these are likely sources of gravitational waves, as in detectable. And so my thought is, okay, well, this is what's been done. We can do better. And we can do better through direct numerical simulation, which I'll talk about. So what happened here was you've got these gravitational waves, which some of them were caused by the primordial turbulence. Some of them were caused by when you have a cosmological magnetic field. You can actually get energy dissipation from the magnetic field as well. And also that changes the dynamics of the turbulence, which can also lead to gravitational waves. There's the vacuum bubble collisions and motion. There are quantum perturbations from earlier on. There's several different things that can go on at or around the time of the early universe, basically from inflation through this first second, which can lead to gravitational waves, which we may be able to observe. And so all of this happens very early on. So the next slide I want to talk about, just kind of do a little review and say, well, what are gravitational waves and why do we care so much about them? Well, gravitational waves, they started off as part of Einstein's general theory of relativity, and it was kind of an initial consequence of Einstein's theory of relativity because if you look at the warpage of space and how this works, if you take, imagine, a rubber sheet, you put a bowling ball on it, it's going to cause the sheet to curve. And the idea is that anytime you put mass in space-time, it's going to cause the space-time to curve around it. So, as a result, if you can imagine you take that rubber sheet, you put a bowling ball on it, and then you take a golf ball and put it next to it, or anywhere else on the sheet, it's going to roll into it. And that effect is gravity, according to Einstein. And so you can just dynamically change the space-time and therefore change the gravity field. So what happens when you take that bowling ball on the rubber sheet and you move it? And you cause ripples to occur in the space-time or in the sheet. And so these ripples are really the gravitational waves. And it's just basically caused by any time anything moves through space-time. So even when you're walking, you can cause slight ripples in space-time that are completely undetectable. So, the idea of general relativity or any gravitational theory is that your space-time is going to tell the matter how to move, and then the matter is going to tell the space-time how to curve. And so if you keep dynamically changing it by moving matter, it's going to cause little ripples. Just like you have a boat and you move it along, it's going to create waves. And these waves are going to propagate out. And these gravitational waves propagate at the speed of light. But the nice thing about them is, since they're ripples in the space-time itself, they don't get absorbed. They just, anytime matter gets in the way of them, it doesn't matter if it's positively charged, negatively charged, or neutral. All matter is going to respond the same way, moving up and down. And, you know, it's just going to happen like that. So this is the way the gravitational waves look. They can have two different polarizations. If you imagine a ring, like a round ring of particles, when a gravitational wave passes by, it can cause it to go in this plus polarization, where it looks like a plus, or a cross polarization. And you can see here that, you know, you can have these two polarizations. You can combine the two to get a rotating polarization, where you have an oval that just rotates. But this is just the basic idea. It's just causing these things to move, and it's causing them to move without really sucking any, without causing these things to be scattered. So this is just a quick review of the difference between gravitational and electromagnetic radiation, and particularly the thing to look at. These are oscillations in the fabric of space-time, not an EM field moving through space-time. They affect all matter the same instead of being, you know, affecting different charges differently. They also, a neat thing is, where electromagnetic radiation is usually high frequency, starts at about a megahertz and goes up 20 orders of magnitude. Gravitational radiation is like sound waves as far as their signal. Up to a kilohertz, it goes down 20 orders of magnitude. So a lot of these gravitational waves are actually, if you could detect them, you could actually hear them. And I think it was Scott Hughes. He actually had a talk he gave where he had a wave signal he generated from colliding black holes, and he pumped it through a speaker, so you could actually hear the collision, and you could hear the frequency of it going higher and higher as they collided. Electromagnetic radiation is emitted from objects that are optically thin, and we have weak gravity. So anything like a black hole or something really massive, no electromagnetic radiation, the light won't even escape. But if you take gravitational waves, they basically come from things that are really massive, where, you know, highly compact objects, dynamical motion of different things. So, yeah.
Expected to be longitudinal type waves?
No, these are transverse waves. Yeah, they're transverse waves, but they're quadrupole in their configuration. So you would actually have, like I showed in the last slide, if the wave is propagating out of the board, this is what you would see.
Oh, so that's the component.
Yes.
Yeah, there is longitudinal component.
Mm-hmm. Yeah, so there are longitudinal. And so the thing about this is that this gives you a perfect way of doing astronomy, because you can have your electromagnetic radiation where you can look at, you know, the bright things out there in the sky where there's really not much gravity going on, and you can have gravitational astronomy where you're looking at the dark side of the universe, the things that don't emit light, and, you know, colliding black holes you're never going to see. Neutron stars, like say they collide and then they give out the gamma ray burst, you might see the gamma ray burst, but you're not going to see the collision before that, because there's no light, unless they're pulsars, which you might get something from it. And then you can put the two together in a case like, you know, colliding neutron stars or colliding pulsars. But the nice thing for us with this is that if we're trying to observe gravitational waves, that study the early universe, they weren't scattered, and so they are propagating from the first second of the universe up until today. We observe them, and we're seeing directly what happened then. And they may be incredibly weak, but they're still there. And so the sources of these gravitational waves are all basically things that we don't know much about. So there are binary black holes, binary neutron star systems, supernova explosions, stochastic sources, cosmology, which is what the focus is here, and exotic sources. And a lot of the work in numerical relativity is basically focused on these compact sources here. And actually, until you really got into GRMHD, where you actually have the fluid as well as having the gravitational part of the code, it was really focused on the binary black holes. They weren't even able to really do much with neutron stars or supernova explosions back then. And so you can see that there's all these different things that can produce gravitational waves, like cosmic strains. You hear about them and you've heard of them, but you never see them. The reason why you don't see them is because they don't emit light. But there's something where if a cosmic strain were to interact,
Could be because they simply don't exist.
that could be too. But the thing is, if you go into a dark room without a flashlight, how do you know the rats and roaches aren't there?
No, actually, it should be like in terms of emitting energy. For example, in supernova explosion, I usually see that why it is really difficult because almost there is an explanation for loss of energy in supernova explosion. But for binary neutron stars or the stuff, if they have some missing energy, they cannot account for it.
Yeah, and that's the thing. They're actually, the whole thing that really got the gravitational wave thing going was in '69, Taylor and Haas, they found a binary pulsar system. And when they looked at it, and they looked at it in spiraling, there was missing energy, which could only be explained by the emission of gravitational radiation because it wasn't emitting any kind of electromagnetic radiation. And, there was just nowhere else the energy could have gone. They weren't in contact, so there was no heat energy. So it was things like that you need gravitational waves for. And so this gives you it's another astronomy when you can really detect these things. So this is basically how you detect the gravitational wave. This is the most common method right now. There's actually...
Has that actually gotten any positive results?
Yeah, that was like the same thing. Actually, what they did was, the plan was always for the ground-based detectors. And I go through a little bit. No, let me explain. For the ground-based detectors, there's a lot of issues with it. One is that because of seismic noise, you can only go from like 10 hertz up to like a kilohertz, which means that the only thing you might be able to detect is solar mass black holes if they happen to be interacting, and your range is very limited. So when they built this thing initially, they didn't expect it to do any real observation, and they thought they were lucky to even detect a wave. And so they really weren't that surprised that, like, so far the supercomputers crunching the data haven't been able to identify anything and correlate it.
Sure, the others found.
Yeah. That's a different story.
Today, nobody can claim that.
So far, nobody can claim that they've detected it. The only thing that they could say is they've proven that they exist because of the missing energy from binary pulsar interaction, the Taylor Haas, which won them a Nobel Prize. So. But the Nobel Committee's wrong.
It is difficult to make a detector because, for example, for electromagnetic waves or most of the systems we have in the detector where the process can take place. If with the gravitational wave, it becomes very hard technically to make a detector which can discriminate all of the effects as compared to this.
Well, also, yeah, that's been the biggest problem. And what the idea was, they built LIGO to be able to kind of test the technology. And before they were even done building it, they already had some upgrades upgrade LIGO 2 already planned, or advanced LIGO. And so they still have not been able to do the full upgrade to advanced LIGO. They've been mostly working on tuning down the noise, because if you look at it, it's got two arms at right angles. When a gravitational wave passes by, one arm's going to get slightly longer, the other one's going to be shorter. This is held in a vacuum, but it's not cryogenically cooled because of other issues with the magnet, with the mirrors. So this is room temperature, so you get thermal noise. Then these magnets have to be suspended, and there's little things that you don't notice, like if you have a rope and you suspend something from it, little fibers in a rope rubbing together, would be enough noise to wipe out the entire signal. And then there's seismic noise, and then there's, at this point, somebody walking by has their own little gravitational wave, so that could actually throw off the detector, or a car driving by. And so really what they're looking for here is a signal strength, delta L over L, is something on the order of 10 to the minus 21, which for 4 kilometer long arms is 1/1000th the diameter of an atomic nucleus. So this is like saying you're looking for super, super precision, and you're not going to just build a super, super precise machine that's never been built before and expect it to work. You have to kind of evolve the technology to make it work. So they have one of these in Louisiana. They have another one in Washington, actually two in Hanford, Washington, of which one of the detectors, they're actually looking at pulling the equipment out of there and sending it to Australia and setting up that system there. There's one over in Pisa, Italy, and there's...
Well, you've heard the Tensor thing for this population.
Well, we'll see after Congress meets. But so far, yeah.
Australia's a bad place for the kangaroos.
Oh, yeah, kangaroos that keep most of innovation. They actually have one in Tokyo that they were actually trying to build, and that's a really bad place.
I hope that wavelength is not longer than the size of the moon.
Well, if you look at this, if you look at this delta L over L, to get a tenth of a millimeter, you need a 3 light year long arm. So this 4 kilometers is pretty cheap compared to that.
And they thought about doing something in space.
Yeah, that's what I'm going to get to. And also, there's a couple other ways of doing this. This is a ground-based detector. Like I said, the limitation is you've got to go 10 hertz and higher. But the real problem with that is that the frequency of gravitational waves scales with the size of what's producing them. So that means if you're going high frequency, you have to look for small sources, which are going to produce small signals. If you want to get the big sources, you got to go low frequency, and those are going to produce stronger signals, which means you got more likely to see something. The problem is on Earth, you get too low a frequency, seismic noise is going to kill you. And so you've got things like a microseismic peak, which is at, I think it's like a 0.6 hertz, where at that frequency, that's where the waves keep hitting the coast, and it'll completely wash away the signal you're going to get.
Is anyone doing correlation techniques between all the detectors to reject noise?
Yeah, that's a good question, and yes, they are doing that. That was actually one of the first things they had to set up, was actually doing correlation, because if you just have one of these detectors by itself, the data is meaningless. You have to have your one in Louisiana and your one in Washington. They both detect something, and that's when you can say you've got something. And then hook this in with the network with Pisa, hook it in with the one in Germany, hook it in with the one in Australia, and you have this whole worldwide network. And then also by telling when they detected the signal, that can also tell you exactly where the signal is coming from. And you can triangulate the location. And then when you can do that, you can do some real astronomy, because you can actually not just detect it, you can tell the characteristics of it, you can detect the polarization of it, etc. And so this is one technique for detecting gravitational waves, and I'm going to get to, but the only one that we care about is this. And this is LISA. And for laser interferometry space antenna. And this was actually gotten a pretty good review as far as being one of the big NASA science missions. And it's supposed to be, going up hopefully within the next couple of years. So the idea here is you have 3 satellites flying in formation. and they're shooting laser beams between them. And so it acts like two interferometers, like one here and one here, so that it can do its own triangulation of the signal. It can you can put a bigger arm length because they're in space, and space is cheap up there. So you can have more sensitivity than you can get on Earth. And another thing is you can reduce a lot of noise because you don't have seismic noise up here. So where LIGO went from like 10 hertz and up, LISA is going to be like on the order of like a microhertz up to maybe a hertz. So it's going to go after the low frequency regime.
How far the sunlight are?
About 500,000 kilometers. No, 5 million kilometers. Yeah, so it's right here, like right around the Lagrange point, 20 degrees behind the Earth.
How they can ensure that station keeping is so precise to avoid noise?
They got a bunch of NASA guys to work on it.
Well, then ESA just announced last week that a technique that they can ensure they're keep the pointing at each other.
Yeah. But anyway, it'll
work as well as gravity growth.
Well, the thing about this is that like the sensitivity's higher. It's about 3 orders of magnitude more sensitive than the ground-based LIGO, and that's to start with. They've actually got an advanced version of this going from there. And with this thing, when I was in grad school, we did some calculations on it. And as far as sources go, if LIGO is looking for solar mass black holes, this is looking for collisions of supermassive black holes, like the ones in the middle of every galaxy. And so when you see galaxies colliding, that's two supermassive black holes colliding. And you see stuff falling into them, that's called quasi-normal modes in supermassive black holes. So if you're talking about supermassive black hole collisions, this thing has a range greater than any telescope on the planet. As far as it can see anywhere in the visible universe out to the horizon that we have from the length of time that the universe has been around. So you can literally, from here,
You can detect gravitational waves.
you don't not just detect them, but you can actually get some detail.
Right. I mean, it's not an optical electromagnetic.
No, it's not an electromagnetic. This is just purely detection. There's another technique which is kind of new. I should also mention it's called pulsar timing to detect gravitational waves. And what they do with pulsar timing is they have radio telescopes set up around the world, and they just monitor pulsars. With the idea that there's a pulsar, it's a regular clock, and all of a sudden there's a tiny delay in that. Meanwhile, 90 degrees over, there's another pulsar, but its signal gets there a little bit sooner than normal. Then what's happening is there's a huge gravitational wave pass by. But as you increase your arm length, you decrease the frequency you're looking for, so that's down in the nanohertz range. And that's like super, super, super low frequency. So there's different techniques, but LISA, for what we're doing, is really the one to go after. Because any of these gravitational waves from the early universe, they should be detectable with LISA.
If you go to the frequency, like nanohertz, that the period is 10 to 9 seconds. So you have to wait quite a good amount of time to wait to get something that makes sense.
Yeah, and that's why with pulsar timing, you can't just do it with a couple pulsars. You actually need to have pulsars in pretty much every part of the sky, and you continuously monitor all of them in order to do that. And then you have to have a really good computer network set up to coordinate the data. But the nice thing about it is you don't have to build any infrastructure to do it. You can basically use existing radio telescopes to do it. So like I said, this goes from around 0.1 hertz to around 1/10,000th of a hertz, less than a millihertz. So what we're doing, or what I'm doing here, is basically want to be able to calculate the most accurate spectrum possible for this gravitational waves produced by primordial turbulence. And really, we've gotten to the point where doing this analytically is just not going to cut it. I mean, they can get a rough idea, but there's a lot of things that are missing. And I kind of went over that. There's, basic dynamics, which is missing. Because one thing that's interesting here is that these turbulent plasma can produce gravitational waves, but then the gravitational waves can also interact with the turbulent plasma and excite modes in the plasma. So there's a back and forth reaction that can go on, which is really, that's a nonlinear effect, which is not captured in any of the analytic techniques.
The only reason why gravitational will go back to the plasma is because it's something like incredibly high density.
Well, we're talking about in the early universe, we're talking about very, very high densities. As you decrease the density, that effect decreases, and so it doesn't do as much. Also, it needs to have a strong magnetic field to couple with, and as you go later in time, the magnetic field gets weaker, and that becomes less of an issue. Another thing is that they're using non-relativistic plasma for a lot of their models. They're using non-compressible fluid for a lot of their models. They're not taking into account dark matter, which could also be turbulent. And so there's a lot of things that I think are wrong with the existing model. That you can, and all these things you can address in a direct inertial simulation. Another thing is you can effectively test cosmological theory at the electroweak scale by basically running the simulation with different initial parameters and then kind of capturing the spectrum of the gravitational waves produced by it. And then eventually, when LISA's flying, you can compare the results to what they're getting. So you're just kind of creating templates and, cataloging all of them. And then, when the real one comes out, that's when you can see, well, it looks like this, so it must be, these conditions must be right. And there's a lot of conditions you can mess with, like the strength of primordial magnetic fields is going to have an effect.
So trying to work on the stationary time-wise. Then probably what I'm thinking is that if instead of electroweak scale, we go to then unified scale, because at that time, energies are at the then radiation scale. Then using supersymmetric models, there is something which is called waves, wavy interacting matter particles, which are only can be accommodated in 2D models.
Yeah, but in order to do that, we really need to get some prediction of gravitational waves produced by that.
Yeah, but electroweak will have more like, electromagnetically interacting particles, even all the,
No, but as far as like the vacuum bubbles and stuff, those are mostly produced during phase transitions, which is on a electroweak scale.
Well, one of the things that you can do with this study is that you can just forget about all of this creation of this stuff about axions and dark matter, and just say, I've got the equations for the gravitational field, Einstein's equations. I have equations that are all consistent plasma. Nobody's ever solved them before. Maybe there is something in the nonlinear dynamics that will help explain what's going on when you don't need to drag in all of these particles.
Yeah, that's another thing I was thinking about, is that there's a lot with the relativistic plasma as far as its dynamics that's really not understood, because it's really not been studied. And, people have studied, or have done more with, plasma that interact with more regular, but like I said, the big problem with what's been done before is that they really weren't looking at the dynamics of the relativistic plasma. They really didn't know. And so they've got something like the Kilgore spectrum that they would use for all their models as far as the energy cascades, but that's not a relativistic plasma.
I think the hypothesis is that you don't need all of that knowledge done, and that if you just push the existing known verified equations, that you will achieve levels such as nonlinear relativistic plasmas interacting with gravitational field, that your hypothesis may explain some of the quantum fluctuations. For that reason, it's worth looking for.
Yeah. And then again, like I said, this interaction between the MHD turbulence, especially the relativistic turbulence, and the gravitational waves. And also, one thing I've noticed in a lot of the papers is they basically try to do some hand-waving argument of saying, oh, well, there are no shocks in this. Because, you could have relativistic shocks in the fluid, and if you do, then they're going to have some pretty significant effects. And so I think it's just a bad thing to just kind of take it out as a possible thing.
Supercooling of relativistic plasma to relativistic Hall effect. And there is another thing. But that is the type of mechanism which could have occurred at that time, and it could have emitted something during that supercooling process. Because jumping from, in cosmology, we don't know what happened in between electroweave and cut scale. That's a big region which we don't know. And then the kind of thing which we could develop.
Yeah. That's something much, much later on. Right now, we're basically just, we're trying to, we don't want to jump all the way back to the very, very beginning of the universe. We're already taking a big leap to get down to this stage. There's a lot of physics, like, kind of like John said, that it's just not well understood before we even get to something like that.
So this is not a very late, it is near electroweave scale, which we are doing for the starlight, or something like that.
Yeah, but I mean, also we're talking about, we'll see. Because we're talking about, probably much hotter, but probably less dense than what you talked about.
Concentrate like highly long Dallas large-scale structure. That's what you're with, basically. That's what you're equating to nature.
Yeah.
Anything else is just dragged in is sort of superfluous.
Yeah.
Dragging in, the microscopic time scale.
Yeah, I mean, I just kind of threw that into the side note, even though it's not really the initial thing.
I spent about 30 seconds talking about it, saying all this stuff is based on linear theory, and we're moving on that and over to the new.
Yeah. Okay. Now. Okay. So now, the basic approach of this work is simulate the early universe after the inflation event. And at that point, we're outside of the inflation event, so we're not too early, because we don't really want to have to deal with all the quantum effects directly. We want to be able to put in sort of our guess of what the initial conditions look like. At that point, the universe, you had a turbulent homogeneous plasma field. You had dark matter in there, presumably.
I do argue about it.
Yeah. And then you got magnetic fields that were around, and the way the magnetic fields were back then is basically the way they want to calculate what the magnetic fields were back then was to kind of do measurements of large intergalactic magnetic fields, and then shrink them backwards in time and say, well, they should have, if they're like this big now, they should have been this big in the past, like that much bigger. And so nobody really knows much about these fields or when they started or where they came from or anything. And part of this work can kind of, if you go back and kind of answer a question about how strong these fields were, you've got gravitational radiation that was produced earlier on. And so you can kind of pick and choose different parts of this. Like we could just study the turbulent homogeneous plasma and take all this other stuff out. Or just put this in with the magnetic field.
The magnetic field is typical in the side of the magnetic field.
Well, if you get rid of the magnetic field, then
you said it was calculated by looking at the galaxy and then extrapolating back then. Is that really you need that big numbers?
Well, the thing is, if you get rid of magnetic field completely for something like this, you can just end up just with a fluid, not a magnetic field.
I'm not saying it's real thing. Is that critical that it is so big for what you out of.
No, but we don't know what it is, though.
Well, the study.
There's like 20 different orders of magnitude.
The reason why I'm asking is that you're saying, okay, well, look at the galaxy and then separate it down. But if you look at the dynamic theories of the Earth, nobody knows really what's happening. In a ball that is compressed that much, it could be anything and the opposite. That's far as we know. So it is not necessarily true that because we see the galaxy that's making this magnitude right now, and you make it exploding, then everything is scaled down.
Well, this is
proportionally.
no, but this is the way that it's only been calculated. Because nobody had any other way to calculate it.
Right. I mean, it's just one.
But the thing is that like they basically had to put in some number, and it's the best way they could do it. And
For
that,
the Earth, resistivity is
It's 2 o'clock.
yeah.
You start out tends to lose magnetic energy quickly.
Yeah.
In an ideal magnetic field, turbulence, magnetic energy is always greater than kinetic energy.
Right.
And so as you get closer and closer to that realm, which may be, very large scales, it starts to get to it, you would expect to have turbulent magnetic energy to be larger than turbulent energy.
Yeah.
So the assuming that there are magnetic fields there is perfectly in keeping with what we know about, ideal energy.
Right. I mean, and it makes sense that they would be there. The question is how big, and that's sort of an unanswered issue because they could be anywhere from 10 to the minus 29 gallons, and they could up to like 10 to 12
The
gallons.
question is not just magnetic fields, but turbulent energy.
Yeah. Yeah, and the turbulent energy, if you assume that the turbulence is caused by these vacuum bubbles, we can pretty much come up with pretty decent numbers as far as what the initial turbulence looked like at that point. Now, as far as our calculation goes, you can use relativistic GRMHD to do the calculation. And that's one reason why I'm doing this, is because, we don't have to invent new equations to make this work. And I'm starting around t equals 0.01 seconds because, the conditions look pretty favorable at that point to be able to use sort of classical or semi-classical everything. And I mean, technically, we could probably even go back further, or we can, if you go too late, then you kind of miss all the interesting physics. And so this is just a quick view of the space-time variable. So this is the metric tensor which describes the curvature of space-time. And so we have this broken up into a lapse, which is the just saying how you evolve forward in time. 3 metric, which is a function of position and time, but it's only in 3-dimensional space. And a shift, which defines any coordinate shifts that occur between hypersurfaces. And then the extrinsic curvature, which is essentially just the time change in 3 metric. And then to make this more stable, we use the BSS and evolution variables, where if you just evolve these 4 components, you get something unstable. But if you evolve the BSSN, where you're actually taking these equations and you're breaking up the evolution equations into a strongly hyperbolic form, then you get a stable evolution. So computationally, it ends up costing us more, but we end up getting something much more accurate that's not going to crash on us. So essentially what we did was we got a solution at this time, t, and it's described by some hyperbolic equations, and we evolved each of the variables up along some normal to the hypersurface, an alpha, and then we apply a coordinate shift, and then we get a new solution. And then we just keep doing this again and again and again, and it evolves the differential equations. That's the ADM formulation, but this actually model works for anything. So even if we're using, instead of the ADM using BSSN, it still works. And it's just that this G would apply to all the assume the curvature is 6. And then if you break it up into BSSN, you're actually evolving, let's see, phi is one variable. This is 6 more here. This is 1 more, so that's 8. There's another 6 that come from this, so that's 14. And then there's 3 more here, 17 variables. And those, only made up variables that are convenient for calculation. Well, anything physical? Well, it's not physical, it's mathematical. Right? And what happens is first off, one thing I've noticed in the stable versions of these evolution equations, a lot of work has gone into figuring out how to evolve these equations precisely, is that when you get the hyperbolic form of the equation, there's no second derivative in the right-hand side of the evolution equation. And so they've kind of gotten rid of second derivative terms. And so they have things like this, where, if you take the derivative of this, you have to have the first derivative. If you take the derivative of this, it's a second derivative term. So you want to avoid those second derivative terms. And so I think in order to get to the full modified BSSN equation that I'm using, I think we probably added like maybe a few more variables onto this. So we might actually be up more over 20 variables that we're evolving. And that's just for the space-time part. That's not even counting the matter field. So for the matter field, you've got basically you've got your mass density, and you can see each of these has this gamma term, which is the 3 metric. You're taking the determinant of 3 metric, and the lapse. And then you got the momentum density, energy density, the magnetic field, and then you evolve these, and then you can also see you evolve this 3 velocities calculated from these. And then you've also got this term, which is sort of like your time component of the 3 velocity. Does that make sense? It's like the 0th component of 4 velocity. And then you've got pressure, which we're calculating using a gamma law equation of state. And so for an ultra-relativistic system, gamma here would be 4/3. And so the way this works is essentially you've got that first set, the BSSN equation, which involves the left-hand side of Einstein's equation. They give you, the Riemann or Ricci tensor. The right-hand side here is basically evolved by the matter field. And so you've got to kind of evolve all these variables at the same time where you're making a change and updating your space-time, plug those in to your matter field, update the matter field, then using that to update your space-time. So you're continuously evolving all this stuff together. And, in the end, you've got like 30 different things you're evolving. And in order to get this stress energy tensor, you have to have these 4 velocity terms, and you have to have, in this case, something like enthalpy, which depends on epsilon here, which is a specific energy. And so in order to get that, we actually have what we call a primitive variable solver, which is basically using a Newton-Raphson method to take those matter variables we evolved and squeeze out values for the 4 velocity and the specific energy, and then plug those in to get the stress energy tensor, and then use the stress energy tensor back into.
You don't have the equation of the pressure or the temperature.
Well, the pressure is coming from this gamma law equation of state. So if we know specific energy and we know rho, then we can get that. And the temperature, I was getting from specific energy. So if you got the specific energy, you can kind of estimate temperature. And in the magnetic field, we use this kind of a 4 magnetic field. for some of the variables. So we've got our initial conditions where we're assuming that the observer, you have to kind of choose a gauge, so we can choose an observer, and we say that they're co-moving with the fluid. So our lapse is actually it's not going to be scale factor, it's actually going to be unity.
Go back a minute.
Yeah.
The pressure, though, you have to either get the pressure or the specific energy density somehow.
Yeah. Well, yeah, we get the energy density from the Newton-Raphson solver.
That's just the numerical method for solving the
Yeah.
equation.
Yeah, but you have an initial value to start out with.
Typically, when you do a magneto fluid or magneto gas, you have to have a general density equation, velocity equation, and temperature for specific energy.
Yeah. But this is the density equation. Or we have a density equation.
That's just a definition.
Right. Yeah, I didn't actually put the equation.
You have to have something like a polytropic transformation.
Oh, yeah, we do. Yeah, we have that.
Well, when you say so,
Well,
say pressure is equal to some power of the density.
yeah, and I didn't put it up here. I've got it. Anyway, yeah, we do have a polytropic equation of state that we use for this. You need to know the Yeah. But yeah, it's well, in let's see. When we start off with this, we're assuming actually this should be 1. So this is just the what they call the geodesic slicing, which is basically just taking our space-time and slicing it up into pieces along the time direction.
What is the meaning? Co-moving with the fluid?
Well, basically what that means is that the if you didn't have you're basically choosing an observer because you're choosing a gauge at which to observe the space-time.
So you were in the magnetic field somewhere away from the ball and then looking at things that.
No, we're right in the middle of the fluid.
On the ball.
Okay. So all the plasma and everything is surrounding.
But right. Depends where you are. You can move in a different way.
No, but that's
the grid.
Yeah, the co-moving grid. Yeah. So there are parts of the fluid that may be moving in different directions.
Like the ship.
The grid is moving, but the
turbine.
Yes, sure.
But it depends on where you are. It's different things, right? You can move in a different way.
There's a relativistic transformation. It's just that the equations are unstable, like David said, unless you do these funny tricks.
Right.
You didn't have a set grid.
Yeah.
Well, no,
You can't have a synchronous coordinates.
Exactly. So you can move with I mean,
Well, it's more than that.
The grid is
Grid is moving with various velocities with respect.
So this is a non-inertial frame where the observer is moving with everything. So you could be accelerating and going back and forth,
Yeah.
I don't know.
Well, yeah, the thing is, you don't want the fluid, you don't want to have current. Like, you don't want to have a current dominating the entire thing. So you don't want to have, like, the plasma moving past the observer, for example. You want to be able to have the observer where they're sitting there and sort of like the center of mass of the system.
And that will be in the middle also of the universe.
Yep. We're all in the middle of the universe.
No, really, I mean, like, no going anywhere.
But the thing is that's the whole idea. Right.
People do
No, if the fluid's moving like this, the observer's sitting in the middle, and they see fluid moving that way and that way. Oh, yeah, you are, because the thing is that the fluid, you you don't know if that whole fluid is moving or
And
not.
there are some equations that are
Think of it expanded.
All right, well, think about it like this. Imagine, our solar system is moving around the galaxy, right? From where we're sitting, we're moving with the solar system. So we're not saying what's happening outside of the solar system. I could change the frame and say we're going to stay right here, and we'll see our solar system moving away, in which case that's not us moving with the system. So that's what I'm saying here. That we're moving with the system. Okay. So we're also at T equals 0.01 seconds. The temperature of the plasma is around 100 billion degrees. It's just easily in the relativistic plasma limit.
On temperature.
Yes, assuming that it's all the same temperature right there. Well, I mean, the universe is pretty close to the same temperature within 3 degrees Kelvin. I mean, less than 3. It's about 3 degrees Kelvin anywhere in the universe you go. In the vacuum, it's just there's tiny little fluctuations in the cosmic microwave background radiation, which are on the order of like 10 to the minus, 5 or 10. So you can pretty much assume that your whole fluid is at that temperature. And then you have a mass energy density that you start out with. The universe is radiation dominated. You can, assuming that, this is the time we're talking about, you can calculate the half parameter of the time.
Radiation dominated versus
What?
radiation dominated versus
Matter dominated. It's in cosmology. It just describes how the universe expands. So if you put what happens is the energy density of the universe dictates the expansion and how the scale factor of the universe changes. And so if you make it a radiation-dominated universe, it's going to expand differently than if it's a matter-dominated. So this is the radiation-dominated era of the universe. And thermal energy, or if it just has to be energy. I know. I mean, just saying it like it's hot.
right, but then cosmic either emitting higher infrared or as particles.
Yeah, it's dark blackbody radiation. So you get thermal. Yeah, and so what happens is, if you have like a matter-dominated universe, like let's just say you start off with this GRMHD code, and you just fill your entire space up with just matter that's cold, then what will happen is you can actually see the space-time itself contract, and it'll collapse because of gravitation. In this case, if you have a radiation dominated, what that'll do is it will actually cause the universe to expand like it's supposed to. So the model fits within cosmology. If you assume the age of the universe is 13.7 billion years, then the scale factor of the time is 2.1 times 10 to the minus 11. And so that means that it was about 100 billion times smaller than it is now. And we need this because a lot of things have to scale to the current day for a data to be applicable. So if you detect a gravitational wave and it's got a wavelength of 1 meter in this time, that scales it up to about 100 billion meters. Because everything got stretched out over time. And then, you define our specific internal energy from our temperature. We calculate the pressure. The electric field is set to 0, again, because of the co-moving condition. The magnetic field, from what we know of, should be less than 100 Gauss. I mean, this is 100 Gauss would be the extreme end.
That specific internal energy epsilon is an initial condition.
Well, yeah, we have to have something to start with.
So you actually assuming a number of epsilon.
Yeah.
T equals 0, T equals whatever.
Yeah, T equals, yeah.
Is that a critical choice, or does everything change depending on that?
Yeah, because it basically, if you choose the wrong epsilon, that would imply a different temperature for the initial universe. In which case, if you've got a universe that's not 100 billion degrees, but it's like 30 degrees, it's going to make a huge difference here. It would be the difference between your universe expanding like it was supposed to and just collapsing on you. And the plasma, how it would work. So it is, a lot of these initial conditions are really critical that they're right, and if they're not, then they don't reflect a realistic universe. Then we define our initial space-time by using the Robertson-Walker metric, which, you know, for the length of the simulation, this isn't too critical because the universe isn't going to really expand that much, so this may not make too much of a difference. But the idea here is we can put in a scale factor which kind of defines how big the universe is and how much it's expanding. And then we also have this term here, which is the perturbation, which is going to be the gravitational wave. So if we put in initial gravitational waves, it would go here. But what's going to happen is, in order to extract gravitational waves from the system, it's actually easier to do it here than it is to do in most numerical relativity. Because in other numerical relativity, you have to apply a lot of tricks in order to get the gravitational waves out of the system. With us, it's basically a homogeneous system. So we can just subtract out the background of what's going on, and what's left over is perturbation. And that would be the gravitational waves. And then, you know, there's all these other things you can do with the, if you want to put an initial gravitational wave into the system just to play with it. Now, there was some work that was done by a couple different people where they basically looked at, you know, they tried to look at, for example, the spectrum of gravitational waves in the early universe caused by inflation. And so one guy did a model of that, and then another person basically said, well, if you have a certain string theory or grand unified theory effects, then you get a birefringence in the gravitational radiation. So some work that I did with a student before involved basically seeing if there was this birefringence, could you tell by just looking at the spectrum of the energy? And the answer was no. But, you know, two reasons I brought that up. One was to just kind of just highlight the work we did. And another one was to show you this plot where you could see that this is the gravitational wave spectrum predicted by that just one source. And this is the bandwidth for LISA. And so you can see that according to this calculation at least, LISA should be able to see some of these gravitational waves from the early universe. I don't have one like it for the MHD turbulence that's predicted, but that's something else that would be very interesting. So the way the numerical revolution works, we have our GMHD equation. We use a modified version of the BSSN, which is strongly hyperbolic. We use the relativistic MHD equations to calculate the plasma. We have a Newton-Raphson solver which recovers their primitive variables like energy, specific energy, and pore velocity. And then we use that to basically evolve the system. Meanwhile, I've written the code in such a way that we can utilize any differencing method since all the differencing is done outside of the primary loops. So we can change finite differencing. We can modify to use a different type of finite differencing, like just different orders of differencing. We can obviously put in a spectral method if we wanted to, if we needed more accuracy, but didn't care as much about the speed. But right now, since we're evolving like 30 different equations simultaneously, speed is an issue, and we have to use like this strongly hyperbolic form, which is the only thing that keeps us from crashing the space-time part. So this is just a quick overview of how the code works. We're using Cactus for this, and the way it works is basically you put in a parameter file which tells you all your initial conditions. It tells you about how dense the plasma is, the temperature of it, what the initial space-time looks like, what differencing method you're going to use, how you're going to output your data, how big your time steps are, everything you can think of that you need to tell your code is going to be in this parameter file. So you load it in, usually with a scheduler or a supercomputer, and the code will actually parse this parameter file and activate the different thorns that need to be done. And different thorns might be, some of them might be controlling the input-output for the system. Some are going to control what type of time integrator you're using. Some are going to control the different parts of the physics and the initial data. So these different thorns are going to do their thing, and they're all going to run through a scheduler, which is going to...
Do the thorns run as threads within the signal process, or are they independent processes?
There are, within each thorn, there are several different subroutines. So they can be running within, actually the way it works computationally is that there's a computational grid that it sets up, like you imagine a cube. And then it literally takes the cube and slices it between them. And it can pass variables between these guys. So you can have part of the code written in Fortran, part in Fortran 90, part in C, part in C++, and they're all sharing the same variables. And these variables, like the grid variables, are actually set to be based on the size of the grid. Yeah. Well, there's actually one executable in all this.
What stage is it?
This is running and testing. So all of this stuff with Cactus has been done. What I did was I wrote thorns handles specifically to GRMHD.
But your code and what you're planning to do, your code is already finished.
It's a matter of running it, putting in the right initial data.
So, have you published anything on design and the application and validation, B&B of it?
Yeah, actually, I had something submitted, and they came back and they said they wanted a few more code tests. So basically, I have to go back and run some shock testing on it, and it was around the time when I had to start on my proposal, so it was kind of parallel projects type of thing. But yeah, you're right. But yeah, this is the thing that always comes up. You go through. I developed a lot of the code while I was doing sabbatical. Because what I was doing initially was, there was a thorn from the gravitation group in Germany, which handled the BSSN, and I tried to write a thorn which basically just did the GRMHD and hooked onto their thorn. And then what happens is somebody makes a change, and the thing updates, and the next thing you know, your stuff doesn't work anymore. So I said, forget that, and I just wrote my own from scratch, which uses my initial data that I want to put in there, which uses my own version of the BSSN, which is actually based on a strongly hyperbolic method versus theirs, which is just the standard, and which does all the other stuff and integrates into my my code better. So I have full control of all the physics thorns, which I've written. And so I've written it, I've run it for some tests, and I'm going to show you some of the results from the runs in a little bit. Yeah, I know. So, this is the scheduler. You do your startup, run the initial data, and then it steps through this pre-step evolution, post-step analysis process for where each one of these can be calling different thorns to do different things within that. And then after so many, it terminates. And you get to, Cactus is a nice tool because it lets you say what subroutine is going to fit in what time bin, and everything is very well organized to make it flexible. So the data analysis part, I've already tested the code against a approximate analytical solution, which actually showed how initial gravitational waves should impact the plasma field. And the next thing I need to do is shock test the code. We're actually putting relativistic shocks into the initial plasma field, and that actually would be in a flat space-time. want to perform a spectral analysis of the output in order to get the spectrum of the gravitational waves or any other interesting variables. Periodic. We want to be able to run at several different scales to get the full range of the spectrum. We want to have different templates for different initial conditions to eventually test against LISA. And eventually, when LISA flies, we hope to have some templates to compare against the data they actually receive. So the way this approximate analytic solution I'm going to show you the results of works is that they assume a flat space-time, and they're perturbing it with linearized standing gravitational waves. Then the time scale of the evolution needs to be pretty short so that the space-time doesn't collapse on you while you're doing the evolution. That ruins everything. And the region of interest is going to be shorter than the radius of curvature of whatever you're dealing with. So this is the results. And you can see here that this is my error versus time. And I just looked at the velocity, density, magnetic field in all the different directions. You can see they're pretty small. I mean, we're talking about, here, less than 5% error in the code. Well, I only ran it, here you don't show the results up to this far, which is just a little bit of time. And the reason why is because a numerical dispersion going on as well. And you can see here, this is the numerical versus analytic for density. And you can see it at first, the numerical and analytic are right on top of each other. And then over time, there's sort of a drift where this is got short time. Yeah, actually, the short time is actually only up to like somewhere in here. But as you go, the further you go, the more drift you get. And so it ends up, like here, the error is like next to nothing. But then if you get all the way out here, it looks like a pretty significant error because, you're out of phase. If you go through the periodic box, only use this like method. I would like to, but the problem is in integrating a spectral method into the cactus code, there's several problems with it. One is that, to parallelize, you use something like FFTW. And FFTW, the way it parallelizes a spectral method or for Fourier transforms is it would actually have to take the box, the computational grid, and slice it along the z direction into a bunch of pieces. Well, Cactus, what they do is they slice it this way and then this way and then this way for each processor. So you have to kind of actually sort of try to use a regridding technique to do that. And then another problem I ran into with it was that in order to do the periodicity and in order to do the communication between cells, Cactus uses something called ghost zones, where they might have something periodic where instead of it going from here, looping around and coming back to here, that last point is missing. But that last point is equal to that point. And with FFTW, when it sees that, it doesn't think it's periodic. And it treats it as if, okay, well, that's not periodic. So I ran into a case of something where I tried using a regular Fourier spectral method, and it didn't think it was periodic, so it didn't work. And then I tried using a non-periodic method, and that didn't work either. So I had it for something that was neither periodic nor non-periodic. What would that be? And so that's what I did last summer. So with that, I ran into an issue, and you're right. I mean, spectral methods would be much better than finite differencing. And my initial thought on this code was to get it to use spectral methods. But, and it's still the architecture of the code is such that eventually, when we solve the problem, we can actually slap in a spectral methods for the.
How does this behavior reflect the error that you publish results?
As far as I can tell, it fits in pretty well. I think Yeah, well, the guys who actually developed this BSSN, or not the BSSN, but the GRMHD code and semi-analytic solution, they seem to have something like that going on in their code text. Seem to, from what I read. I mean, I'm thinking that they didn't want to come right out and say, hey, look, we have this numerical.
There's something published in like mathematical physics where someone has put these error tests to numbers.
I haven't seen it. Well,
my numbers are just the same as their numbers.
Yeah, that's what I did when I looked at the guys who actually wrote this semi-analytic, and I looked at their results, and I looked at their initial conditions they put into it.
Like they do a numerical test.
Yes. Yeah, and that's what I went by.
So numerical test is like something like yours, if you're because that's one thing that I guess reviewers will want to say, because it's hard to tell whether the errors are expected or unexpected unless you have so many errors.
Yeah, and that's the thing is that's what I was able to go by. But it seemed like they were running it also for a very short time, and I noticed that some of their results they were starting to see bigger errors in the end. And so I think that they didn't come right out. What?
Energy conservation.
As far as I can tell, there isn't an energy conservation issue. This is completely.
Take a look at energy at the beginning of your run and calculate the energy after the run. How would it compare?
I don't know. It's not easy to do with this because you basically here to calculate the energy within space-time, it's a really complicated thing because you're looking at the energy of the space-time curvature, and then you're also looking at the energy of the plasma. So it's not a trivial calculation to do. There's no expression of space-time? No, because you have to basically integrate over the curvature of the space-time with a non-uniform metric. And so that would involve, it's not exactly the calculation. Basically, we calculate the ADM mass of the. Yeah. I mean, we could try to figure out some way of doing that, but it's not a simple test. No, it's not a simple test.
Well, yes, it's simple numbers.
Yeah. It's simple numbers to look at.
Because you say my energy is off by 0.3%.
Yeah.
Well,
what we do is, but what we do is we actually have these things in what's called like the Hamiltonian constraints or the momentum constraints, and these kind of represent something analogous to conservation of mass and energy without actually calculating the full mass and energy.
Now, in your equations, you're always going to put in conservation form.
Yeah.
But is your numerical method actually on with?
Yeah, and in our case, when you do the Hamiltonian and momentum constraints, numerically they're never exactly satisfied, but they're pretty small deviations. And I have those numbers. And actually, I have those numbers in the graph of the paper.
But generating these in complex form, some quantitative integrated, sure conservation.
No, because what happens is usually in the numerical relativity, what they'll do is these constraint variables are calculated on the fly. They're not really put back in, and so they're not really forcing everything to follow constraints. And there's been a lot of debate on whether or not they should, because sometimes if you force them back in, then you get artificial things going on.
Well, this is very determinants in energy and other invariants as a monitor of how stable it's almost.
Yeah, and
could force it to almost be constant, like this, normal how that's not losing power.
Yeah, so what we do is we use it as kind of a monitor, but about these constraint violations, then it kind of, you have to translate it into, okay, what is a big number? And that's never been really accurately put in. At what point is it too big?
What happens with the turbulence simulations is you can make that observation very, very good, but you have to make the time step really, really, really small. And it takes you 10 years to do it once, so you don't do that.
Yeah.
So you have to do something that's sort of optimal. You get a 0.1% variation or 0.505% variation over a million time steps.
Well, see, with this, it used to be even worse because when you had the, before they came up with the DSSN equations and figure out stuff that was strongly hyperbolic, you think you could make the time step smaller and get a more accurate code, when in fact you're doing the exact opposite. And the code would actually crash faster if you made the time step smaller. And the errors are coming faster because you were actually getting constraint violating modes and other error modes that would literally come into your system as high frequency modes and they would never dissipate.
So you know, why do we do this?
You know, like I said, there's so many variables running around that there's some really interesting mathematics going on, and it gets to that point where it's just so much numbers you just can't keep up. But yeah, like I said, this is actually, from what I can tell, this is actually a pretty decent result given that counter drift. And
so that's the job of enough leads is to fail.
Yeah. And I mean, and the thing is that they didn't have any problem with this as much as they said, well, where are the shock tests? You know, where, that
Because there's easy target. Well, let's crash test dummy tests.
Well, you know, and it makes a lot of sense here, I guess, because initially I thought, you know, we really didn't need the shock test.
Because unless you put in something to solve the shocks or to smooth out a little bit, that will cause some crashes.
Mm-hmm.
You know, you keep going into the slope. You have to have something that captures it or resolves it.
Yeah.
Or, you know, and so there are ways to do that. But,
yeah, I'm sure we will. So that's one thing on the agenda. So in the future, want to be able to visualize the data a little better. And this is sort of a wish list item right now. Do the shock test, have better initial conditions that are more accurate, you know, more realistic of the universe. One possibility adding viscosity, and this also includes magnetic resistance too. And there's a way of doing this by essentially just modifying the stress energy tensor. So that's it.
Good.
Okay.
Okay, so this is all sort of pulled out.
Yeah. I mean, a lot of things here I probably you know, phrase it differently than the way they are in the proposal, but this is essentially what we're doing. Okay. So Chris, you still there? Chris says the images are a bit distorted on his screen. Thanks for the presentation. He just has no mic.